Human ideas are abstract, hazy, and subjective. Scientific proof requires absolute precision. Crossing the gap between a theoretical concept and an undeniable fact requires compressing assumptions into strict, measurable evidence. The core challenge facing all researchers is determining how to legally translate an abstract theoretical construct into a mathematically provable reality. You do not guess. You force raw observations through a strict, uncompromising mechanical pipeline. This pipeline operates in sequential stages. Researchers must structure raw datasets, apply predetermined statistical laws to process the information, and carefully navigate the zero-sum trade-offs of research validity. Without successfully surviving this rigid architecture, any resulting research conclusion is simply an opinion masquerading as science. This represents the foundational unit of empirical research, the dataset matrix. Horizontal rows map to your exact unit of analysis. Each row represents one distinct subject. Columns slice through these subjects, representing specific variables being measured. Their intersection creates individual data points. Translating an abstract concept, like trust or satisfaction, into a measurable column is a process called operationalization. Researchers use single or multi-item scales to turn abstract ideas into concrete metrics. This pyramid illustrates the measurement hierarchy. Nominal data sorts observations into distinct buckets with no mathematical order. Ordinal data ranks into ordered categories with unknown distances. Interval data features equal distances, but lacks a natural zero. Ratio features equal distances and an absolute zero. A variable's position on this measurement hierarchy dictates the absolute limits of what a researcher can mathematically claim. Selecting a statistical technique is a predetermined law of mathematics, not a researcher's creative choice. This matrix routes independent variables on the left and dependent variables on the top toward their only valid output. Comparing two categorical groups against a metric outcome dictates a t-test. Expanding to 3 or more categories routes to an ANOVA. A fatal professional pitfall is manually running multiple t-tests instead of a single ANOVA to compare several groups. This artificially inflates statistical error and corrupts the dataset. Combining two top-tier metric variables triggers regression analysis, used to predict or explain exact numerical outcomes. Researchers apply advanced layers of control, like ANCOVA, to these models. ANCOVA acts as a mathematical filter, scrubbing out the noise of secondary covariates to isolate the main effect. They must also account for interaction effects, where the mathematical impact of one independent variable depends entirely on the hidden presence of another. Statistical tests are highly specialized lenses. Forcing the wrong mathematical lens onto a dataset guarantees a distorted, invalid reality. Correlational research observes relationships as they naturally exist. Causal research requires the deliberate manipulation of variables to test strict cause and effect relationships. Warning tone. Observing that two variables move together does not prove that one caused the other. The 4-step causality flow is an uncompromising security checkpoint to prove cause and effect. First, covariation. Variables must move together mathematically. Second, logic. There must be a rational explanation. Third, time. The independent variable must happen before the dependent variable changes. The final and most frequent point of failure is step 4, the no-z rule. Variable z represents a confounding variable, a hidden alternative cause. If another cause explains the relationship, the causal link breaks and the final gate slams shut. Failing even one of these 4 gates demotes a scientific breakthrough back to a mere coincidence. Even if the mathematics and causal logic are flawless, the entire pipeline collapses if the measurement tools themselves cannot be trusted. Reliability is pure consistency. It is the ability to get the exact same measurement repeatedly, regardless of whether that measurement is right or wrong. Researchers use internal consistency, often assessed with Cronbach's alpha, to ensure multiple items within the same survey instrument are locked together, measuring the same underlying idea. But a perfectly consistent tool can still deliver completely inaccurate data. This scatterplot demonstrates validity, true accuracy. Valid instruments measure exactly what they claim to measure, and nothing else. A valid measure will naturally be reliable, but a highly reliable measure is not automatically valid. Building a study on a highly reliable but invalid dataset yields conclusions that are mathematically flawless yet entirely false. The ultimate tension in research design exists between the competing forces of internal validity and external validity. Internal validity is the raw power to rule out alternative explanations. It relies heavily on strict, sterile lab environments. This diagram illustrates how labs block specific threats, shielding data from biological maturation over time, testing effects from prior measurements, or mortality effects where participant dropouts skew the final numbers. Maximizing this internal control generates pristine causal proof, but it completely isolates the data from the way humans actually act in the real world. External validity is the ability to generalize findings outward to diverse, chaotic real-world populations and settings. Forcing higher lab control inherently destroys realism. Increasing realism destroys causal control. When physical lab control is impossible in the field, researchers must compensate by using statistical control methods. Statistical control acts as a mathematical filter, directly scrubbing extraneous variables from the analysis to salvage internal validity. Flawless research is an illusion. Rigorous science is the deliberate, calculated balancing of these pipeline constraints to extract a truth we can finally trust.